So, thanks everybody for coming. It's my great pleasure to introduce Sven Pistre from RWTH Aachen. And he will talk about the radon transform and higher regularity of surfaces minimizing a Finsler area. Please.
Hi, thank you for the introduction and thanks for the opportunity to talk to you about my work today. First, let me say, please, if you have any questions, feel free to interrupt me at any time. And if you're interested in the slides, then use your smart device to scan this QR code, or just the old school way, just send me an email. So today I will talk about parts of my PhD thesis, which is supervised by Heiko-von der Mosel. And there are a lot of words in the title of my talk that probably warrant a little explanation. So I'm going to give you an outline of the talk. So first I'll introduce what Finsler geometry is about, just very broadly, and I'll introduce a minimization problem that I consider. And then in the second part of the talk, I will very briefly introduce a framework which was, first considered probably by Morey, and then generalized by Stefan Hildebrandt and Heiko-von der Mosel in the 1990 to 2009 about so-called Cartan functionals. And then I will show you how my minimization problem fits into this framework. And in this framework, there are a lot of results about existence and regularity of minimisers of such variational problems. And in the third part of the talk, then I would show you what are the main ingredients to apply this Hildebrandt and von der Mosel framework. Okay, so let's start with some notation. Most of the results that I would show you will work out nicely for general manifolds M immersed by an immersion or an embedding F into an ambient manifold N. But then in the end, in the application, the result will always be that I have a disk, a two-dimensional disk, immersed into Rn. So it will be a disk type surface of high codimension. And so the new thing in this thesis is that I can generalize results that were previously known for two-dimensional surfaces in codimension 1 to high codimensional 2D surfaces. Okay, so what is a Finsler manifold, or what is Finsler geometry about? So generalizing Riemannian geometry, if you have the tangent bundle of a manifold, then instead of having a family of scalar products on each tangent space, you just take a norm on each tangent space, and you propose that this family of norms varies smoothly as you vary the tangent space. So here, for instance, I have a smoothened dodecahedron in R3, and if you assume that if you look at each point of R3 and take the tangent space there as another copy of R3 and maybe vary this dodecahedron in a smooth way, then this will generate a Finsler norm. So by the way, I like to think of norms and scalar products in terms of their unit balls, so that I have a geometric picture. So if I have a scalar product, then the unit ball will always be an ellipsoid, and in general a norm will maybe look like this. Okay. So in more rigorous terms, I just want to show you these definitions, but they're not too important for this talk. So a Finsler metric is then a somewhat regular function on the tangent bundle, which is positively one homogeneous, only positively so. And usually the people in this area, they will say if it's also absolutely one homogeneous, then we call it reversible. but in general, you can think of the unit ball of this norm as being asymmetrical, so it can be blown in one direction. And the third condition on the metric is sort of ellipticity condition, where in one tangent space, in the tangent bundle, you take a flagpole, that's the point xv here, and then on this flagpole, you propose that that there is a scalar product which depends on the flagpole, and then you have a family of scalar products. And note here that this doesn't mean that the Finsler metric itself is a scalar product, but that you can generate a scalar product which depends on this flagpole, on this direction. And so I think what you can do, for instance, if your manifold n is compact, you can average by these flagpoles, and then you actually get a Riemannian metric on the tangent bundle. That's called the Binet-Legendre metric. So there's a connection there. But for this talk, it's not so important. So maybe just have this picture in mind. Okay, so let me introduce to you the functional that I want to minimize later. And that's the Busemann-Hausdorff area functional. So this will be, and in order to define this, let me remind you that if you have a map or immersion f, small f, from some manifold m into n, then you can pull back objects from the target to the domain n. And so here, the Finsler metric that I propose now, it will be on the target, and I can pull it back, and we'll get this object with the bar on top. And also what I will do now is I will take an auxiliary Riemannian structure on the domain M, which will be a G bar here up top. And then what you do is you take the regular Riemannian area functional, or the regular Riemannian volume density, this is this term here, and then you integrate over the manifold, and you say the Busemann-Hausdorff area functional is then this density with a weight function W. And this weight function is defined here at the bottom. And I think it's easiest if you just look at this expression here. So it's a ratio, and what you do is you compare at one point in the tangent space on the manifold. You take the Euclidean unit or the Riemannian unit ball, and you take the Finsler unit ball, and you compare the Riemannian volumes of the two. So that's why you have to take this auxiliary measure, so that you can measure the volume of these objects. And if you do that, then maybe you can see already that if the Finsler metric actually is Riemannian, which would mean that the norm ball at the bottom here is also a sphere, let's say it's the same metric as the auxiliary one, then this weight function is just 1, and the Busemann-Hausdorff area will reduce to the classical Riemannian area. And also note that actually the numerator here will always be a constant. So whichever auxiliary Riemannian structure you take, you will always have that this ball will have the classical unit ball, the classical measure of the unit ball in our M. And I will denote this by this constant omega m. Okay, so basically the functional is the same as the Riemannian one with this density, with this weight in front. And so maybe this appears a bit strange that you have to choose this auxiliary Riemannian structure on the manifold when you want to do Finsler geometry, when you want to not take scalar products. But thankfully, with the definition that I've shown you here, this functional does actually not depend on the choice of the Riemannian metric. So let me maybe lose a few words on why that is. And so the first thing that you have to see is that if you have two Riemannian metrics, or if you just want to think of one fiber of the bundle, then maybe two scalar products, then there's always an isomorphism of the tangent bundle that kind of intertwines the metrics. So that you can write G bar that is somehow related to H bar with this map B. Okay, and well, how do you prove this? If you like coordinates, then what you can do is you look at the gram matrix of G bar, and you look at the gram matrix of H bar, and you take G bar times H bar inverse, and that will be your isomorphism V, and you can patch that together on each fiber of the tangent bundle to get a smooth bundle isomorphism. And if you like more abstract words, then if you have these two Riemannian structures, you get two Ries isomorphisms from the tangent bundle to the cotangent bundle, and then this isomorphism B will just be go up with one Ries isomorphism, let's say of G, and then go down to the tangent bundle again with the Ries isomorphism of H bar. Or in the language of geometry, of differential geometry, it will be the flat operator and the sharp operator of the two metrics combined. So anyway, given two such objects, there's always something that connects them. And then if you look at the induced volume densities and the induced Hausdorff measures on the tangent planes, then you have this transformation formula here, where you will just take the determinant of this isomorphism and the square root of this, and that's how it transforms. And therefore, the ratio that I showed you before, the weight function had this in the numerator here, this measure, and the density here is sort of in the denominator, and the density is in the numerator. So this will cancel. There's a question in the chat here. Can one not simply say the Busemann-Hausdorff area function is conformally invariant? With respect to the auxiliary measure, or the auxiliary Riemannian metric, or what do you mean?
No, I guess I'm just meaning that you can link the two metrics together.
Yeah, that's probably what you do if you take this isomorphism B, I guess.
Yeah, I just wondered if that was a way to encode what you're saying.
Yeah, that's probably a more abstract way of what I wrote down here. Yeah,
thanks.
It's probably what you said. Yeah. Okay. Anyway, so the point is this functional is now independent of the choice of this auxiliary structure. So there's another question. Oh, it seems to be an answer. So the two structures do not need to be conformally equivalent. Okay, all right. Great, so moving onwards then, we have, so we've defined the functional and we want to look at the minimization problem. So here I look at the Plateau problem. And so for those of you who do not know this problem, let me just give you a quick introduction. So here what you do is you're in Rn and you have this boundary curve. This is on the right here now, this boundary Jordan curve gamma. And you ask yourself, is there a surface which minimizes a given functional? So in my case here, the Busemann-Hausdorff functional, amongst all surfaces which span this boundary curve. And so this will be written here in such a way that we can later apply the direct method. So it's the surfaces are W12 functions, and there's this boundary condition, which means it's not too important here, but it means that you can go, as the parameterization goes forward on the boundary curve of the unit disk on the left, you go forward on the boundary curve gamma, and you can stop. So So the Sobolev trace can have a zero gradient at some points, but you cannot go backwards. So that's what I mean when I say weakly monotonically. You can stop, but you can't go backwards. So that's the problem, okay? And now to the second part of the talk. So this is about this framework which considers exactly this Plateau problem for a class of functionals which are called Cartan functionals by my advisor von der Mosel and his advisor Stefan Hildebrandt in works I think spanning from 1999 to 2009. So maybe some of you do not know what a Cartan functional is. So here's a definition. So in principle, what they tried to do is to generalize the classical proof of finding minimal surfaces of Mori, I think. And so they try to look at generalizations of functionals that have the same shape as the classical Riemannian area functional. And the classical Riemannian area functional, if you look at it in coordinates, the density will be, there will be this Jacobian determinant in front, and basically it will be the normal of the surface, and then you take the norm of the normal of the surface. And in high codimension, the normal of the surface cannot be, so this term here, this bivector, will not be the normal of the surface, but it still will be there in the area functional as the term coming from the Jacobian determinant. And so here, a Cartan functional is a functional of this type where I have an integrand which depends on the position in space in Rn, and then it depends on this bivector variable. So in codimension 1, as I said, it's the normal to the surface, and in high codimension it just basically comes from the area functional. And so this parametric integrand is supposed to be continuous, and there are usually three conditions which will be in all the theorems. So first, it's positively one homogeneous. The second one, it's convex. And the third one is a growth condition. So there are two universal constants, two global constants, M1 and M2, such that this growth condition here holds. And this is all in the second argument, so in this bivector argument, positive homogeneity and convexity and growth in the bivector. Oh, and maybe one more word. So the bivector, I will write this down later. It's technically or algebraically, it's element of the exterior power bundle. But what you can do is you can identify this with the space R to the power n choose 2. Okay, so let me not show you many theorems right now. You will see them in the applications, but let me just give you some remarks about these Cartan functionals. So the positive one homogeneity corresponds of the integrand corresponds to diffeomorphism invariance of the functional. So this is a very easy calculation. So diffeomorphism invariance with respect to diffeomorphisms on the domain. So you can take you can change the disk. And convexity and linear growth conditions on C, they correspond to lower or weakly lower semi-continuity of the functional, if you want to apply the direct method. And then these three conditions that they're still visible here, they already guarantee existence of minimisers of this functional with respect to the previous Plateau boundary conditions. And then further conditions, and we will see some conditions later in the talk, will then also yield higher regularity, higher interior regularity of the surface. So interior meaning that inside of the unit disk, the parametrization will be of some regularity, and some other conditions which are usually on the curve in the target, so on the Jordan curve. There's also regularity at the boundary. And I said this before, so lots of these results were investigated in years here, 1999 to 2009. Okay, so now we have at least seen this framework, and so we kind of need to define an appropriate integrand here for the functional that I've invariantly defined earlier. Okay, so let me give this to you here right now, and we'll see why this makes sense in 2 minutes or so. So here now I will take an auxiliary Riemannian structure on the target. So previously it was on the domain, it was a G bar. Now that this is on the target, and I will define a function on this space here. And this is the space this is the exterior power bundle, and this small s here means that I only look at simple m vectors or totally decomposable m vectors, and they are of this form here. So V1, can you see this? Yeah. So they're supposed to only be of this form, and this is well, in high codimension, this is not the whole space. In codimension 1, all vectors are of this form, but in high codimension, that's not the case. And so this space here is not a vector bundle, but it's a bundle of algebraic cones, and that's basically is the main difficulty in high codimension. Anyway, so how is this defined? So here you can see that you take a bivector, so you take a point on the manifold and a bivector spanned by tangent vectors. And here at the end, you can see that this is basically the Riemannian area integrand. It's the classical one. It's the term that pops up when you calculate the Jacobian. And then you have this weight function here, which looks kind of similar to what we've seen before. Only that everything is now on the target, not on the domain. So this is the Finsler ball and the target with an F, not an F bar. Previously it was pulled back. And what do I mean by this object here? So the brackets around the M vector, that's this space here, and that's the space, the M-dimensional subspace spanned by this M vector. And so if you know a little bit about algebraic geometry, maybe you know the Plücker embedding, and so taking the bracket here is in principle is a left inverse to the Plücker embedding. And so I think in principle you can think of for hypersurfaces, you can always take the unit normal and take the scalar product with the unit normal, and that defines the hypersurface. And this is the high codimensional generalization of this. Okay, so now let me show you why this fits into the previous definition. So recall that the first line here is the definition of the functional, and then what can we do? Here we had the unit ball of the pulled back norm, but if we look at if we look at the surface from M to the image, and we take the auxiliary metrics, that they fit nicely, then we see that this is actually an isometric, a Riemannian isometric map. And so then in principle, what you have here is that you have the unit ball of the pulled back norm will just be the unit ball of the full norm intersected by this plane here. And this plane is just the tangent plane of the immersed manifold in the target. Okay, and so that if you calculate everything, then one step further in coordinates fits very nicely. Fits into the definition of the function that I've defined up here. Okay, so here's the function again in local coordinates. This is that one. And well, the thing about this is that you can very easily calculate that this integrand here is absolutely one homogeneous. So we only needed positive homogeneity, but it's absolutely one homogeneous. So maybe this corresponds to the fact that I think you can measure the surface of unorientable immersed surfaces, but I'm not too sure. But anyway, you have this absolute non-homogeneity. And also in the case of codimension 1, there's this result from Busemann from 1949, which shows that you can convexly extend this integrand to the full space, to the full exterior power bundle. And rather recently, Burago and Ivanov in 2012 showed that in the setting that we're looking at, so for m equals 2 and high codimension, this is also the case. So these are the two conditions that we had before. And so then now I can show you an existence result for the problem, for the Plateau problem, which, well, popped out of my master's thesis in 2017. And so in principle, you can now just apply the Cartan framework from Hildebrandt-von der Mosel. And yeah, so what I can do now is I can take a two-dimensional disk and immerse it into Rn in high codimension. And on Rn, I have these two structures. F is the Finsler structure and G is the Riemannian structure. And what I impose now is this growth condition on the Finsler metric. So it says, kind of says that I can globally compare the Riemannian and the Finsler norm. And there is some symmetrization assumption on the Finsler metric, which is here now not too important. Then I have existence of minimisers of this Plateau problem. And I also have, just as in the classical case, that this parametrization is actually conformally parametrized with respect to this chosen Riemannian metric, to this auxiliary one. And we have this low regularity result. So, we have this low regularity result where it's continuous up to the boundary of the unit disk, is Holder continuous on the interior, and you can write down the Holder exponent, which depends on the growth conditions at the top. And you have this higher integrability, this local higher integrability. Okay, so we have this existence result, and so maybe let me show you, well, let me show you some pictures as to how these surfaces might look like. And so this is with calculated with software written by my colleague Henrik Schumacher. So on the right, you will always see the chosen Finsler unit ball, and on the left, you will see at least a numerical minimizer of this functional with respect to the Plateau boundary conditions. So here, this is just the Riemannian case. So it's the sphere, the unit sphere. And on the left, you can see the N-upper surface. And now on the right, I will take an icosahedron, and then you can already see that some strange things here happen. And as I change the metric, it will be more apparent. So if I take the dodecahedron, somehow it appears that there are these smooth ridges here, and you have these flat or somewhat flat surfaces, maybe, which maybe correspond to the unit ball or the dual unit ball. I'm not exactly sure what's going on here. And so here, if you take this octahedron, you get this minimizer. And if you kind of tilt the octahedron a little bit, you get this, you kind of see these shifts in these ridges on the surface. So this is maybe interesting, but I have absolutely no idea what's going on here mathematically. This is just to see what these surfaces might look like. There's a question. Are we starting to connect with the Wolff construction here? So I'm not exactly familiar with the Wolff construction, but I think I've read somewhere that the Wolff shapes of the norms, yeah, that there could be some. I think the Wolff shapes, are they not the polar bodies or something like that?
Yeah. So this is when you have a surface energy which is anisotropic, and faceting is a sort of generic feature when you have a sufficient loss of convexity.
Mm-hmm. Okay.
So it's just interesting to see the images are quite compelling in that sense. You're seeing faceting.
Yeah, that's right. That's
shapes. So just a thought.
Okay. Yeah, I'm happy to discuss this further later. Yeah, thanks. Okay. Right. Going on to the last part. So we want so the question is maybe in these pictures, are these ridges smooth or at least regular, or are these hard cuts? Is it like a Lipschitz ridge? And let me first show you a result from in codimension 1 from 2013 by a previous PhD student of my advisor, and they had a higher regularity result in codimension 1. So they will get this higher regularity, so one further weak derivative, and the first derivative is Hölder continuous. If we impose that the Finsler norm is comparable to the Euclidean unit norm in this C2 sense. So they have a constant, and then if you can compare the Finsler norm and the and the Riemannian norm in the C2 sense, then you get this regularity result. And so what I've been doing is in the last, well, couple of years, I suppose, I've been translating their very coordinate heavy calculations into a more invariant form, and there you can see that most of their proofs will actually go through in high codimension as well. And so this is the result that I will have in my thesis. I will take a disk immersed into Rn, a high codimension, and an arbitrary Riemannian metric on the target, and then I find if I have a constant which depends on the chosen metric and the dimension, such that if I have the smallness condition, this comparability, the C2 comparability, then I get the same result. And so what I would like to have is I'd kind of like to get rid of this linear target space and want to have some generic, well, of course with some conditions on the target manifold, and have the same result. But I don't know if this is possible because this Cartan framework that I showed earlier is very much based on this linear structure of Rn. And I don't know if you can patch together every computation that you do on fibers of the bundles to, well, to some target n. So this is what I want to do. And hopefully, hopefully this epsilon here at the top is not too large, and I can show you my thesis sometime soon. Anyway, so the first ingredient is again from this Cartan framework, is called perfect dominance functions, and this is based on this result from 2003, where if you're back in this general Cartan setting, where, let me remind you, this was an integrand which was continuous, positively one homogeneous, convex, and of linear growth, then you get the desired regularity if further the integrand is of class C2, so it's better, at least outside the zero bivector, and it possesses a perfect dominance function. So this sounds very obscure, so let me define to you what a dominance function is. And I said this before, this whole Cartan setting is trying to generalize this classical proof by Morey, I think, of the area functional. And what they did there was you take the area functional and you have the Dirichlet energy, which is greater or equal than the area. And it's equal if and only if the surface is conformally parametrized. And then you basically perform a minimization of this better functional, this dominance function. And this has better properties. And then in the end, you show that the minimizer that you found there will be conformally parametrized. And so therefore you have in the end also shown existence or regularity results about the area functional. So this is what we're mimicking here. So you have this dominance function, which majorizes the Cartan functional and is equals on the set of on the set of points which fulfill this conformality relation on the right. And further, the property on this dominance function is that you want it positively 2 homogeneous and of quadratic growth. So now earlier the Cartan function was 1 homogeneous and of linear growth, and this is now has that property. And a dominance function is called perfect if it's higher differentiable, at least outside of the zero matrix. Oh, sorry, this is now, I didn't say this. So this is now a function of n by 2 matrices as opposed to bivectors, okay? So bigger space. And the second condition is that you have this local ellipticity result, this local ellipticity condition here at the bottom. So for every radius, there is a constant lambda such that if you take the dominance function and subtract sufficient multiple of the square norm, then this is a convex function on this ball of radius r. Okay, and now the question is, when do such perfect dominance functions exist? And thankfully, there's also another result by the same group of people in 2003, which says that if I have a Cartan integrand, which is good enough, meaning that it's already C2, positively 1 homogeneous and of linear growth with given constants. And further, it's also uniformly elliptic in the sense that now there's a global constant lambda, such that I can take the parametric integrand and subtract this multiple of the Euclidean area integrand here, that this is a convex function. Then there is this lower bound, so there's a number k0 which I can state explicitly, or they can state explicitly, such that for every k larger than k0, this new integrand, which is basically now the original integrand, but you add a sufficient multiple of the area integrand, and this new integrand possesses a perfect dominance function. So this is maybe not exactly what we want to do right now, but thankfully there's this corollary by Radon and von der Mosel in 2013, which says that with the same conditions on C as above, so, and namely C should be C2 and uniformly elliptic, and here you have this C2 comparability of the integrand and the Euclidean area integrand, then the parametric integrand itself possesses a perfect dominance function. Okay, so that's what we would like to use. So we have these three conditions: C2, uniformly elliptic, and this this C2 comparability to the classical result, to the classical integrand. Okay, so let me show you the second ingredient to how you can apply this general framework, and that's the Radon transform. So this comes from integral geometry, and let me show you first what we would like to do. So we would like to have this area integrand, which we've seen earlier. You will see again on the next slide what it looked like. We need to have these three conditions. So the area integrand needs to be C2, uniformly elliptic, and this smallness condition should be, this smallness condition should be fulfilled. And maybe recall that in the main theorem, there was a condition of comparability of the Finsler norm and the Euclidean norm, but in the corollary on the previous slide, the condition was on comparing the corresponding integrands. So what we need to do in principle is, and what you can do is, transform such conditions on the Finsler norm and the Riemannian norm to the integrands, and that's not so hard. But then these three conditions up here will be using functional analytic properties of this Radon transform. So, and if you haven't seen this, let me give you a little motivation why this is useful in our case here. So at the top, I've written, again, written down the area integrand. So where there was this, this ratio in front here, and we will, in principle, now look at the inverse ratio of this and calculate this. Okay, so so recall that these brackets here means that this was an m-dimensional subspace of the tangent space at P in the target. So in the target, you had this auxiliary Riemannian structure G, and so it's a scalar product at point X. And you can now restrict this to this m-dimensional subspace, and you get this Hilbert space. And now you can just use spherical coordinates in this subspace. And what you want to do is you want to calculate the measure of this set here, of the full dimensional ball intersected with this space. And so you will you have a spherical integral over this well, of this restricted, with respect to this restricted interior product, and then you have this radial integration here over the characteristic function. And well, we want to calculate this, and so note that a point is in the unit ball if and only if the norm applied to this point is less than 1, and because the Finsler metric was supposed to be 1 homogeneous, this translates to the displayed condition there. And so in principle, that means that this integral up here doesn't go from 0 to infinity, but only from 0 to this number. And now this is an easy integral. We can calculate the primitive. And so basically the ratio, the inverse ratio at the top, we can calculate is now this term here. So it's a spherical integration of a function. And now the last point that we need to see is that the inclusion map of this subspace into the full tangent space is an isometry, because we've just restricted the scalar product. It's very similar to what we've done at the very beginning. So in principle, we can translate this now to an average integral over the full dimensional Riemannian sphere intersected with this subspace over some function. Okay, so this pops up here, and that's just the definition of the Radon transform. So so just for the donation, for the notation, so the Riemannian is the space of m-dimensional subspaces of Rn, and now I have a linear operator which maps a function on the sphere to functions, which maps a continuous function on the sphere to functions on the Riemannian, and it's defined by by this condition here. So you take the full dimensional sphere, intersect with some m-dimensional plane, and then you integrate the original function small f. And well, you need to first check that this is actually well defined, so that the resulting function is continuous again. Maybe this should be intuitively somewhat clear, that if you have a smooth continuous function and then you vary the plane, then this integral shouldn't vary too much as well, but you need to prove this first. And let me mention here that you can lift the whole procedure that I do here to the sphere bundle and the Grassmann bundle of a general Riemannian manifold, just by patching everything together. We will see in a minute why. And let me just remind you that the previous calculation on the previous slide basically says that the area integrand is now somewhat related to the Radon transform of the Finsler norm to the power minus m, or 1 over Finsler norm to the power n. And then there was this Riemannian area integrand here. Okay, so why do I want to do this? Again, I think I mentioned this before. The downside, at least in my opinion, to using this this area integrand as is that in high codimension, the base space is a bundle of cones. So the base space with these simple vectors is a bundle of cones. It's not a vector bundle. And so it's difficult to handle. And so what I've come to well, realize is that the benefits of the Radon transform here is that the base spaces are, so the sphere and the Riemannian, they're both homogeneous spaces with respect to the same Lie group of orthogonal matrices. And so they have a lot of algebraic and geometric structure. And I've mentioned before that there is this Plücker embedding which somehow which relates the Riemannian and the simple vectors. And so there's a connection between the two formulations of the same problem. It's just different language. But I think the Radon transform here it fits better. Okay, let me show you some properties of this Radon transform. So the first one and the most important one is an equivariance property. So you have the orthogonal matrices which act by rotation on the sphere and which act by rotation on the space of planes. And so this is very nice because what you can do now is if you have, we have this equivariance property here. So you take some orthogonal matrix and it doesn't matter if you take a function and rotate it first and then integrate it over some subspace, or if you take the original function and you just rotate the plane, the result is the same. So that's what I've shown you here with my hands, or at least trying to show you with my hands, is the proof of this equivariance property. Is really not complicated. And this equivariance property, I've mentioned this before, you need to show that the Radon transform is, it maps into the continuous functions on the Riemannian, and there you can use this equivariance. And you also need to lift this to a bundle map. You need to also have this equivariance property. So this is really a crucial property. Okay, so now what you can do is you can take the derivative of this property with respect to Q, with respect to the rotation, and you look at the derivative at the identity in the Lie group. And then what you will get is sort of an infinitesimal version of this equivariance. So that means if I can then show that if I have a function which is already C1, then the transform function will also be C1. And I know how I can calculate the derivative. So this term here is basically the infinitesimal version of the equivariance. And so this fundamental vector field here is the infinitesimal generator of the group action. I've denoted it here by the same symbol on the left and on the right, but they are vector fields on different manifolds. So they're not exactly the same. I just denoted them here for the talk like that, but they're very intimately related. So maybe let me write down what the definition is. So this vector field at some point x is you take the exponential map of the Lie group, and then this is an element in the Lie group, and then you can apply this with the action to this point, and then you look at what happens for t equals 0. You look at the derivative. So this is the definition of this fundamental vector field, and that's the action on both the sphere and the Riemannian. So it's a different object. Okay. So let's go to the next slide. Here at the top, I've just copied this differentiability theorem from before, and what you can do now is you can iterate this, and then you get if you use a very nice recursive, well, it's not so nice, but if you use a recursive formula for the covariant derivative of a function on a manifold, you can show that the Radon transform is a continuous operator from the CK functions on the sphere to the CK functions on the Riemannian, and you can get explicit bounds for the operator. And so all of these results that I've mentioned so far on the Radon transform, they're probably well known to the community in integral geometry, but I couldn't really find them written down in the way that I needed them. So I showed them, I proved them myself, but I'm pretty sure they're known to the community. However, the next result here is something that I could actually find in this very thick book by Sigmundur Helgason, who I think is an expert in these transformations. And so, so this says that the Radon transform is actually invertible on the space of even functions on the sphere, at least. Even functions, because if you have an odd function, then the Radon transform will be 0, because you integrate over part of the sphere, and if it's an odd function, then the integral will calculate to 0. So let me summarize what we needed to do. There were these 3 properties of the integrand that we needed to show, and for the first property, so that the integrand is actually C2, you use this higher differentiability of the Radon transform. And for the second one, you use, for the uniform ellipticity of the integrand, you can use the invertibility of the Radon transform. And for this C2 comparability, you need these explicit operator norm bounds on the Radon transform. And the main difficulty in high codimension was that, at least in my opinion, was that this space of simple vectors is not a vector bundle. And the Radon transform helps very nicely with this, because you can use this Lie group theory and this theory of homogeneous spaces. And so again, this is the theorem, and hopefully, as I said before, this epsilon won't be too big. And with that, I would like to close my talk, and I thank you for your attention.
So thank you very much. Are there questions, remarks, comments? Let's see, that seems not to be the case unless somebody's typing. Okay, then let's thank Sven again. I choose this one.
Thank you.